Hello everyone. Today we'll be going through section 4.4 of Pure Math 2. We'll be looking at the derivatives of natural logarithmic functions, specifically the natural logarithm of x and the natural logarithm of f of x. We'll look at how to prove these derivatives, and I'll also go through a quick example where I will differentiate a natural logarithmic function. So for the natural logarithm of x, we'll consider a function y being equal to ln of x, and then y prime, the derivative of y with respect to x, will be equal to 1 over x. Looking at y being equal to ln of f of x, and an example of this could be y is equal to ln of e to the x squared minus 7x cubed plus 9. In this case, the inside here would be our f of x. And the derivative of this function will be y prime is equal to f prime of x, the derivative of the inner function, divided by f of x itself. Now, we're going to want to look at how to prove the natural logarithm of x firstly. And there are two ways that we can do this. We can do a proof by first principles, which takes a bit longer, but is definitely more rigorous, or we can simply prove this using rearrangement. I'll be proving it using rearrangement first, because it's faster, and first principles second, and we can prove the derivative of the natural log of f of x using the chain rule. Now let's consider our function y is equal to the natural log of x. We can rearrange this, raise both sides to the power of e to obtain x being equal to e to the power of y. Now, we'll differentiate both sides with respect to y here. Dx over dy on the left-hand side will be equal to the derivative of e to the y with respect to y, which of course, as we know, will just be equal to e to the y. Then this function, we can take the reciprocal of both sides, change the left-hand side over to dy over dx. The right-hand side becomes 1 divided by e to the y, and since we know x is equal to e to the y, we can substitute that in here, and our derivative ends up being 1 over x. A very quick proof. Now, for the proof by first principles, we're going to consider the same function, y being equal to ln of x, and we're going to consider what happens as our small change in x to our function delta x approaches 0. I'm going to write delta x as h here, just for convenience. It's much easier to write down. From first principles, we know that our derivative of y with respect to x is going to be equal to the limit as h approaches 0 of y2, which in this case will be the natural log of x plus by h, subtracted by y1, which will just be the natural log of x. All of this divided by x2, which will be x plus by h, subtracted by x1, which will just be x. And the x's in the denominator will cancel. Now, from this point, I would like to use one of the laws of logarithms to combine this numerator over here into one singular logarithm. We'll also rewrite our limit as h approaches 0 as L of h, so these two mean exactly the same thing. It's just once again for convenience. So the law of logarithms that we're going to have to use here will be the law that the logarithm of a divided by b is equal to the log o is equal to the log of a subtracted by the log of b. And we'll simply use this in reverse here. So we know that we'll end up with the numerator with the natural log of x plus h divided by x, and in our numerator here, we will end up with h on its own. Now, from this point, I would actually like to do two things. Firstly, we will separate 1 over h from our natural logarithm a little bit here. It's exactly the same thing. It's just moved around in our writing. And we will simplify this fraction slightly x plus h over x, we can have x over x plus h over x, and x over x will just be equal to 1 plus, plus h over x. And from here, I'd like to use another law of logarithms. I would like to use the power rule of logarithms, where we know that the log of a to the power of b is equal to b times the logarithm of a. I would like to use this in reverse again to put all of this to the power of 1 over h. This will be equal to our limit of the natural log of 1 plus by h over x, all of this divided, all of this to the power of 1 over h. Now, the term inside the brackets here, along with the limits applied to it, is quite similar to our limit definition for e to the power of x. And I'm going to make a quick substitution here. I'm going to let some variable u be equal to 1 over h. This means h is going to be equal to 1 over u. We want to consider what happens as h approaches 0. As h approaches 0, our denominator here gets smaller and smaller. So on the right-hand side here, our number gets larger and larger. We can conclude that u will approach infinity. So we can now rewrite this as the limit as u approaches infinity of the natural log of 1 plus by 1 divided by ux to the power of u. Now, I'd like to look inside here a little bit, because this still isn't exactly the form that we want. I'm actually going to rewrite this a little bit. We're instead going to consider this as being 1 over x, and then all of that divided by u. It's exactly the same fraction here, except this is more easy to consider when comparing it to the limit definition of e to the x. In this case, we're looking at the limit definition of e to the power of 1 over x. And that's very, very convenient. We can simply substitute that in here now and get rid of our limit. This will be equal to the natural log of e to the 1 over x. We can use our power rule here to separate this out. This will be equal to 1 over x times by the natural log of e. And since the natural log of e is equal to 1, we'll have 1 over x multiplied by 1. So our natural log of e simply cancels out of the equation. And we are left with our desired derivative, 1 over x. I'd like to look at the derivative of y being equal to the natural log of f of x next. And we will prove this using the chain rule. So first, we'll consider f of x being equal to some u. We can state that du over dx is going to be equal to f prime of x. And if we consider y being equal to the natural log of u, we can conclude that the derivative of y with respect to u is going to be equal to 1 divided by u. Using the chain rule, where we know that dy over dx is going to be equal to dy over du multiplied by du over dx, we can substitute our terms for du over dx and dy over du into this, and end up with 1 over u multiplied by f prime of x. We can substitute f of x in here for u, and we're simply left with f prime of x divided by f of x, our desired result. I'd like to go through a quick example where I will differentiate a natural logarithmic function. Let's consider the function we had at the beginning of the video. Y is going to be equal to the natural log of e to the x squared minus 7x cubed plus by 9. So for this, we're considering f of x as being equal to e to the x squared minus 7x cubed plus by 9. Then our derivative of f of x, f prime of x, is going to be equal to our derivative with respect to x of e to the x squared minus by the derivative of 7x cubed, which will be 3 times by 7 x squared. 3 times 7 is equal to 21, 21x squared, and the derivative of 9, which is 0. Looking at the derivative of e to the x squared here, we know that this will be equal to the derivative of x squared multiplied by e to the x squared. The derivative of x squared, as we know, would be 2x. So this whole thing works out to be 2x times e to the x squared minus by 21x squared. Then we can conclude that our derivative of y with respect to x will be equal to f prime of x, which will be 2x times e to the x squared minus 21x squared. All of this divided by f of x, which will be e to the x squared minus 7x cubed plus by 9. And there we have it.